Hello, welcome to another module in this massive open online course on estimation for wireless communication systems. So far we are looking at the estimation of a vector parameter, and we have formulated the least squares cost function, and we have derived the maximum likelihood estimate of this vector parameter as the solution or as the minima of this least squares cost function. Alright, and we have explored this vector parameter estimation in the context of a multi-antenna downlink wireless channel estimation scenario. Now let us look at an example of this multi-antenna channel estimation scenario to understand this better. So what we are going to do in this module is start looking at a simple example of a multi-antenna channel estimation problem. Okay, so we are going to start looking at an example of multi-antenna channel estimation, correct. So we want to consider a base station. Remember, we are considering a downlink scenario in which the base station is transmitting to the mobile. So the base station has m equal to 2 antennas, which means there are going to be 2 coefficients or unknown parameters, and the mobile has a single antenna. So therefore, to draw it, depict it schematically, if I were to draw a schematic diagram, it is going to look something like this. I have a base station over here, and that has 2 antennas. So this is m equal to 2 antennas, and the mobile station, your mobile has a single antenna. So let us say this is your mobile that has a single antenna, and therefore naturally I can denote the channel coefficients corresponding to these 2 antennas as one is H1, H2. These H1 and H2, these are your multi antenna. These are basically the channel coefficients which are to be estimated, and that is your problem of. So these are the channel coefficients. H1 and H2 are basically the channel coefficients which have to be estimated in this multi-antenna downlink scenario, and that is the problem of channel estimation. In fact, that is the problem of vector parameter or vector or a channel vector estimation. All right, that is what we are looking at. And the system model for this, again, that is something that we have already seen, but let us give it here again so that you can recall it. I have the received symbol yk or the observed symbol yk equals x1k times h1 plus x2k times h2 plus vk. What is this? This is your the observed symbol. X1k is the pilot symbol transmitted from transmit antenna 1 at time instant k. So this is pilot symbol from TX antenna 1 at time k, and x2 similarly is pilot symbol from transmit antenna 2. So what is this? This is your pilot symbol from transmit antenna 2 at time instant k. So this is the model we are familiar with. So we have the system model yk, which is the observed pilot symbol at time instant k at the mobile, equals x1k times h1 plus x2k times h2 plus v of k. x1k is the pilot symbol from transmit antenna 1 at time instant k, x2k is the pilot symbol from transmit antenna 2 at time instant k, and vk is as usual, that is the noise sample. Okay. So, this is basically again something that we have seen many times before. This is your noise sample or the noise at the receiver. Okay. So, now let us take a look at this. Now, our pilot vector, going back to our system model, our pilot vector at time instant k, this is x1k, x2k, this is your pilot vector at time instant k. This is the pilot vector at time k, and now let us consider in this example, let us consider n equal to 4, let us consider n equal to 4 pilot vectors, and these pilot vectors for instance can be given as x bar 1 equals 5, 4, x bar 2 equals 4, 5, x bar 3, that is the pilot vector transmitted at transmit time 3 is 3, 4, and x bar 4 equals, let us say 4, 3. So, we have 4 pilot vectors x bar 1, x bar 2, x bar 3 and x bar 4, which corresponds to the pilot vectors transmitted at time instants 1, 2, 3 and 4. All right. So, we are considering the transmission of 4 pilot vectors. Okay. So, naturally corresponding to these 4 pilot vectors, there are going to be 4 received symbols. Let the 4 received symbols y1, y2, y3, y4 be. We have in this example y1 equals 2, y2 equals 1, y3 equals 1 and y4 is also equal to 2. Okay. And now, to compute the maximal likelihood estimate of the channel vector H. So, now we would like to, what we would like to do, we would like to compute the maximum likelihood or basically the least squares estimate, the ML estimate of the channel vector. Remember, the channel vector is nothing but basically the vector of the 2 multi antenna channel coefficients H1, H2. So, we would like to basically estimate the channel vector H bar, which consists of these multi antenna channel coefficients H1, H2. So, it is a 2-dimensional vector. So, it is basically a 2-dimensional channel vector or also basically a 2-dimensional unknown parameter vector. So, basically this is a 2D . This is a 2D unknown parameter vector. Now, to find that estimate, let us first give x, which is basically your pilot matrix. Remember, this is x, which is your pilot matrix. So, let me write this clearly again. X is x bar transpose 1, x bar transpose 2, x bar transpose 3 and x bar transpose 4. This is basically your pilot matrix. So, this is what is this? This is your pilot matrix x. from our formulation of the channel estimation or the multi antenna, which is x1 bar transpose is 5 comma 4, x2 bar transpose 4 comma 5, 3 comma 4, 4 comma 3, and as you can see, this is basically a 4 cross 2 matrix, or basically n cross m. Remember, we said that the pilot matrix is an n cross m matrix, where n is basically your number of basically the number of transmitted pilot vectors, which n is equal to 4 in this case, and m is the number of unknown coefficients, m is equal to 2 in this case. So, the pilot matrix is n cross m, that is, it is a 4 cross 2 matrix X. Okay. Also, let us now form the observation vector y bar equals y1, y2, y3, y4, which is basically 2, 1, 1, 2. This is basically, this is your recall y bar is your observation vector. This is basically the observation vector, and the ML estimate now is given as ML estimate. Recall that the ML estimate h hat of channel vector h bar, also basically your LS or least squares estimate. Remember, the ML estimate, the maximum likelihood estimate, is also the least squares estimate, is given as h hat equals x transpose x inverse x transpose y bar. So, first let us compute x transpose x. So, x is a pilot matrix. Let us first compute this quantity x transpose x inverse. Okay. So, let us first compute x transpose x inverse. First we will compute x transpose x and then compute the inverse naturally. So, proceeding in steps, I would like to first compute x transpose x inverse. Now, x transpose x transpose is the transpose of the pilot matrix, that is equal to 5, 4, 3, 4, 4, 5, 4, 3 times 5, 4, 4, 5, 3, 4, 4, 3. This is equal to, you can simplify this is 66, 64. This is a 2 cross 2 matrix. Note that this is basically your m cross m matrix is 66, 60. I am sorry, this is 64, 64, 66. Therefore, the inverse of this 2 cross 2 matrix, the inverse of a 2 cross 2 matrix has a standard formula, that is 1 over the determinant, which is basically 66 square minus 64 square times interchange the diagonal elements and negatives of the off diagonal elements, and 1 over 66 square minus 64 square is 1 over 66 minus 64, that is 2 times 66 plus 64, that is 130 times 66 minus 64 minus 64, 66, which is now cancelling the 2. I have 1 over 130 times 33 minus 32 minus 32, 33. Okay. So, now basically what we have found is, we have found this quantity x transpose x inverse. X transpose x is a 2 cross 2 matrix. We have computed the inverse of this matrix, okay, where x is the pilot matrix. Okay. So, what is this? this is basically your x transpose x inverse. Now, the other quantity that we need to compute is basically x transpose y, and that can also be computed as follows: x transpose y bar equals 5 4 3 4 4 5 4 3 times 2 1 1 2, which is basically equal to this vector 25 23. This is 2 cross 1 vector. You can all see clearly this is your m cross 1, or basically your 2 cross 1 vector. And now the channel estimate h hat equals x transpose x inverse x transpose y bar. Remember, this is your maximum likelihood estimate, which is basically equal to, now substituting for x transpose x inverse, I have 1 over 130 times 33 minus 32 minus 32 33 minus 32 33 times the vector y bar, which is 25 20 23, and this is basically what we are saying is this is your x transpose x inverse and this is your x transpose y bar. And therefore, now I can simplify this further. This I can show, this is basically 1 over 130 66 plus 23 23 minus 64, this is basically 1 over 130. I am simplifying your estimate of the channel vector 1 over 130 89 minus 41, which is basically, now if I have to write this, this is 89 by 130 minus 41 by 130, and this is basically your h hat. So, what we have computed is we have computed basically this quantity h hat, which is the maximum likelihood estimate of the channel vector h bar for this multi antenna downlink channel estimation scenario with 2 antennas at the base station and a single antenna at the mobile. Okay. And therefore, now this quantity you can see, this is basically your h1 hat, estimate of the first channel coefficient, and this is basically your h2 hat. So, therefore, h1 hat equals 89 by 130, h2 hat equals minus 41 by 130. Now, further, if the noise is IID, let us say, let us consider Gaussian IID noise of variance minus 3 dB. So, we are considering independent identically distributed Gaussian noise samples of variance. So, the variance is minus 3 dB implies 10 log 10 sigma square equals minus 3, which basically implies sigma square equals 10 to the power of minus 0.3, which is approximately equal to half. So, minus 3 dB noise variance basically implies that sigma square is approximately equal to half. And remember, from this I can compute the covariance matrix. The covariance matrix for this multi antenna channel estimation scenario is sigma square x transpose x inverse, right. So, the covariance, remember the covariance matrix of channel estimation that is your expected value of h hat minus h bar times h hat minus H bar transpose, that is basically equal to, we have already derived the expression for that in the behavior of the maximum likelihood estimate, sigma square x transpose x inverse. Sigma square we have calculated is half, x transpose x inverse also is something that we have calculated before, that is 1 over 130, 33 minus 32 minus 32, 33, and this is basically equal to 1 over 260, 33 minus 32 minus 32, 33, and therefore now I can write this as the 2 cross 2 matrix. This is your covariance, which is basically equal to 33 over 260 minus 32 over 260 minus 32 over 260 and 33 over 260. What is this? This is basically the covariance matrix. This is your covariance of the maximum likelihood. This is the covariance of the maximum likelihood estimate, which we have calculated as sigma square x transpose x inverse. Okay. And now we also said from this covariance I can extract the variances of the elements. Remember, recall, this is variance of H1, this quantity, this is variance of H1 hat, that is expected value of H1 hat minus H1 whole square equals 33 by 260, and this in fact the second the I comma ith diagonal element is the variance of the ith channel coefficient. So, this is the variance of H2 hat, which is the 2 comma 2th diagonal element. So, that implies that expected value of H2 hat minus H2 whole square is also equal to 33 divided by 260. All right. So, basically we have calculated the covariance and we also calculated the variances of the individual channel estimates. All right. So, this is basically a simple problem, all right, a simple problem which illustrates the application of the maximum likelihood estimation procedure or the least squares estimation procedure that we have developed in the context of basically a vector parameter estimation scenario. So, all right, we have developed the least squares parameter estimation problem, and we have shown that the least square solution is given as H hat equals x transpose x inverse x transpose y bar, where x is the pilot matrix, y bar is the observation vector, and we have considered this simple channel estimation scenario for 2 antennas at the base station and a single antenna at the mobile, and considering n equal to 4 transmitted pilot vectors. We have derived the maximum likelihood channel estimate, and we have also derived the covariance of the channel estimate and the variances of the individual channel coefficients. All right. So, this example illustrates, simple example illustrates basically comprehensively the computation of the least squares channel estimate as well as the covariance and the respective variances. All right. So, we will stop this module here and continue in subsequent modules. Thank you very much.